All right, welcome back to the fourth video in this module, which hopefully represents the end of the material that will be in the first live class, but broken this up into pieces so it's a little more digestible online. So at the end of the last class, we were talking about this notion that quantum physics tells us that we have to be able to combine particle and wave behavior in the same object, right? And that we have things that behave like particles and waves at the same time. And the experiment that proves that this is a real phenomenon is basically adding together two different sources of things that are doing this and seeing behavior that's both characteristic of particles and waves. So we imagine, right, this experiment where we shoot footballs at a giant wall with slits cut in it, and what we see on the far side is two stripes of places where we get lots of footballs, one corresponding to balls that went through the left slit, the other corresponding to balls that went through the right slit. If we do the same thing with things that are purely waves, what we see is something like this pattern from a bee caught in water, where the waves add together and either make really big waves or no waves at all, depending on how exactly they come together. And at the very end of the last video, we talked about this experiment doing this with electrons, where we see the electron behaving like particles. They're detected at a particular point, at a particular instant, but also like waves in that all of the many detections collectively combine to trace out a pattern that's characteristic of wave behavior. Now, at the end of the last lecture, I also threatened that there would be some math. So this video is going to go through this in a little more detail and explain, exactly why is it that you get this kind of pattern, right? What is it that we're seeing in these things, and why do we get the pattern of bright dark stripes that we do, mathematically speaking? So we're going to go back to our idea of mathematical waves, and we're going to think about this starting in one dimension, where the waves are traveling left to right. It's a single sine wave pattern, and I can write this as a wave function that looks like some amplitude times the sine of kx minus omega t. It's got a wavelength, it's got a frequency, it's traveling left to right through one dimension of space. Now I want to ask what happens if I have not one source of waves, but two, right? I'm going to add together two different waves. So both of these waves are going to be sine waves traveling left to right. And so I have, phi1 from the first light bulb that's a sine kx minus omega t. And I need to know, what is the second one going to look like? Well, in principle, right, it's going to have the same form, right? It might have a different amplitude, might have a different frequency, different wavelength. But I want to fit this in here, right? I'm going to look at some point off to the right. I want to look at the wave pattern that results when I add these together, right? I can describe that second one as originating not from x equals 0, but from x minus d, right? Because the waves from that second light bulb, right, that second source of waves, those waves have traveled slightly less distance, right? They're less by the separation between my two sources. Now I want to make this as easy as possible, so I'm going to think about two waves that have exactly the same wavelength, and they have exactly the same frequency as a result, and they also have exactly the same amplitude, because that's just going to make my life much simpler. All right. This is like the situation of the bee, right? The bee is flapping its wings, right? The wings are flapping in unison, so the waves produced by each are going to have exactly the same frequency, exactly the same wavelength coming out, and so it's a much simpler problem mathematically. When I do that, what I have is I want to add these waves together, and I have something that looks like I can pull out the A, right? It's the same amplitude for both. I have a sine of kx minus omega t, and I have a sine of kx minus d minus omega t. All right. I want to add these two things together. I can do this. There's a bunch of trig identities. You have to remember, sine of a plus b and sine of a minus b and all those kinds of things. You can do this as a bunch of algebra. I'm going to skip right to the answer. The answer is a formula that looks like this. You can see it looks like twice the amplitude of the single wave, so it's a bigger amplitude in principle. And I have a piece here that looks like a traveling wave. I have a sine k times some stuff with x's in it minus omega t. But the stuff with x's in it, now it's this x plus x minus d divided by 2. It's sort of the average distance, right? We're taking a wave pattern as if it originated halfway between the two sources. Okay. But other than that, this looks just like a traveling wave, right? This is a sine wave pattern that's moving from left to right, has some wavelength, has some frequency. But now I have this other term in here, this cosine that shows up. Cosine of k times d divided by 2. Right? This is a cosine that only depends on the distance between the two sources. Right? It doesn't vary in time. So this is, you can think of this as just modifying the amplitude. Right? And what does this do? Well, if I change d, right, if I make d equal to 0, so both sources start at the same place, then cosine of 0 is, well, it's 1. Right? So I just have a wave that's twice as big. And that makes sense, because if both sources start in the same place, it's just the source of waves that's twice as bright. Right? Now, if I make d a little bit bigger, right, this d is going to go through oscillations as I make it bigger and bigger. Right? If d is equal to, you know, a wavelength, then this is going to end up with a pattern that that cosine is going to be equal to 0. Right? That cosine term is going to be equal to 0. I have no waves at all. That corresponds to destructive interference. But if I make d bigger, right? If I let d get bigger and bigger, it's going to come back again. Right? So there'll be these points at when k times d is equal to 0, when k times d is equal to 2 pi or 4 pi, right? Where the amplitude will be twice as big as either of the individual waves. That's constructive interference happening. On the other hand, if k times d is equal to pi or 3 pi or 5 pi, right, any of those odd multiples of pi, then it's going to be 0. Right? And so so I have this interference behavior. I have both constructive and destructive interference. It just depends on the separation between the sources. Right? This tells you the essence of these interference phenomena in situations where you have waves that are really traveling. Right? It just depends on the extra distance that one of them has to travel. Now, to look at the experiments that we're talking about, we really need to expand this out into 2 dimensions, not just one-dimensional waves. But I can conceptually do that pretty easily if I think about this situation of a barrier with 2 slits in it. Right? If I look at the pattern that arrives on the screen on the far side, what I'm going to see is it's going to vary depending on the distance away from the line through the center of the slits, in a way that, again, depends on the extra distance that one of the 2 waves has to travel. So there'll be some spot right in the center, right, exactly midway between the 2 slits, where these waves are guaranteed to arrive perfectly in sync with one another because they've each traveled exactly the same distance to get there. When that happens, then the peaks land on top of the peaks, and I get really big waves. Right? If I'm talking about light waves, I'm going to get a really bright spot there. Right? But if I move a little to either side of that, right, I move a little bit up, say, the wave from the lower slit in this figure has to travel some extra distance to get to the screen. And when it does, right, that extra distance means it goes through part of another oscillation. If that distance is just right, if it's half a wavelength extra distance, then the waves arrive with the peaks of one and the valleys of the other, and I get destructive interference. I get a dark stripe. But if I go further, right, that extra distance that's traveled increases, right? And as the extra distance increases, it eventually reaches a full extra wavelength. And when it does, now the peaks of one wave and the peaks of the other are on top of each other again. Right now, it's the 27th peak of one wave and the 28th peak of the other, but it doesn't matter because the pattern repeats itself perfectly. These are going to add constructively and get me another bright stripe. Right. So this pattern is what gives us these bright and dark stripes that we see when we do this double slit experiment, whether it's with electrons or whether it's with light. Now, you're going to have a little bit of homework in this class, and the assignment from this one is going to be basically to work out this pattern here in terms of the angle at which you observe these spots. And to do that, you need a little bit of right triangle geometry here. So I have this figure shows you 2 slits that are spaced by some distance d, right? And the question is, what is the extra path length that one of them is going to travel in terms of that distance d and the angle, which is also the angle that you'll see on the screen a long ways away when you detect it. This is going to be a homework problem. that would be defined in much more detail in the homework assignment that you can find on Nexus. The key thing to take away from this, though, is that this is going to give you a pattern of bright and dark stripes that is exactly the thing that we see when we do this double slit experiment with electrons. Right? We do this experiment with electrons. We send the electrons at a barrier with slits cut in it. Each electron is detected on the far side as a particle at a particular position at a particular instant in time. But collectively, all of the electrons together trace out this pattern of bright and dark stripes that's exactly like the pattern that you get from adding together waves that have passed through both slits, right? Waves that are coming together and doing this constructive and destructive interference. This is the essence of quantum physics right here, these particles behaving like waves at the same time. Now, the thing you can ask is this something peculiar to electrons? Right? Is there something magical about electrons that this works for? The answer is no. You can also do this with much, much bigger things. There's a group in Austria that's made a really nice career for themselves out of just demonstrating this wave interference with larger and larger objects. And so they started out with these buckyballs, these 60 carbon atoms arranged in a shape that looks a lot like a soccer ball. And if you shoot those at a barrier with slits cut in it, what you see on the far side is a pattern of bright and dark spots, right, of peaks and valleys that reflects the interference that's happening between these things as they behave like waves. So these very large molecules, the 60 carbon atoms, still behave like waves as they go through barriers with slits cut in it. And I can do this. You can do the same thing with even larger things. This is even a few years old now, but this is that same group doing this with big floppy organic molecules or long chains of carbon atoms. Right. I can't tell you the names of any of these things, but what I can tell you is that this largest, floppiest one here has 430 atoms in it. Right. 430 atoms in these big long chains. Those things behave like waves and interfere with each other to produce this interference pattern on the far side of a barrier with slits cut in. So this shows that really this quantum business of particles behaving like waves happens for everything. Everything in the universe behaves like a particle and like a wave at the same time. And we can demonstrate that experimentally using this phenomenon of interference. That's the end of the material that's going to be in the first live class. Might be in a slightly different order in the live class, but this topical breakdown I think will work a little better. Next time we're going to talk about how this joint particle and wave nature leads to the phenomenon known as tunneling. And that'll be the subject of the second live class and the next set of 3 or 4 videos here. So stay tuned for that.